Hello learners, welcome to the course Statistical Methods for Economics, Theory of Estimation. In this session, we will discuss the concepts related to understanding what is estimation, methods for estimating unknown population characteristics based on sample data, know how to assess the quality of an estimator, to make informed decisions based on the predictions made using sample data. In the previous module, we have discussed the concept of certain probability random sampling techniques such as systematic random sampling, cluster random sampling, multi-stage random sampling, and multi-phase random sampling. The process of selecting the samples, its advantages and disadvantages, and its application in various fields have been discussed in detail. In this module, we shall discuss the concepts related to estimation theory. Introduction. The theory of estimation is a branch of statistics that deals with the process of making inferences about unknown population parameters based on a sample of data. The goal of estimation is to find the most accurate and the efficient estimate of the population parameter based on the sample data. Estimation is a crucial aspect of statistical analysis as it provides a framework for making predictions and decisions based on the available data. There are different techniques and methods for estimation, including point estimation, which provides a single estimate of the population parameter, and interval estimation, which provides a range of values that are likely to contain the population parameter. The choice of estimator depends on various factors, including the type of data, the distribution of the data, and the level of precision desired. The quality of an estimator is assessed through measures such as bias, variance, and mean squared error. The theory of estimation is widely used in various fields, including engineering, finance, medicine, and social sciences, to make informed decisions about predictions based on sample data. We shall now look into the various terminologies associated with estimation. Parameter: the unknown value of a characteristic of the population that we are trying to estimate. Examples include the population mean, population proportion, or population standard deviation. Sample: a subset of the population used to make inferences about the population parameter. Estimator: a statistic that provides an estimate of the population parameter. Sample estimate: the point estimate of the population parameter calculated from the sample data, such as the sample mean or proportion. Sampling distribution: the probability distribution of the sample estimate, assuming that the sample was selected randomly and independently from the population. Point estimation: the process of finding a single value as an estimate of a population parameter. Interval estimation: the process of finding a range of values that are likely to contain the population parameter. Bias: a measure of the difference between the expected value of an estimator and the true value of the population parameter. Unbiased estimator: an estimator that has zero bias. Variance: a measure of the dispersion of an estimator around its expected value. Mean squared error, a measure of the quality of an estimator equal to the sum of the squared differences between the estimated values and the true values of the population parameter. The mean squared error is abbreviated as MSE. Maximum likelihood estimation, a method of finding the estimator that maximizes the likelihood function, which measures the probability of obtaining the sample data given a certain set of population parameters. Bayesian estimation, a method of estimation that incorporates prior knowledge and updates it with the sample data to find the posterior distribution of the population parameters. Characteristics of estimators. The following are the criteria that a good estimator should satisfy: unbiasedness, consistency, efficiency. We shall now look into each one of them in detail. Unbiasedness. In the theory of estimation, unbiasedness refers to the property of an estimator where its expected value is equal to the true value of the population parameter being estimated. An estimator is considered unbiased if, on average, it produces estimates that are not systematically too high or too low. An estimator Tn is equal to T of x1, x2, etc. xn is said to be an unbiased estimator of gamma of theta if expected value of Tn is equal to gamma of theta for all theta in theta. Unbiasedness is an important property of an estimator as it provides a measure of the accuracy of the estimator. If an estimator is unbiased, it is more likely to produce accurate estimates of the population parameter. However, being unbiased does not guarantee that the estimator will produce accurate estimates in every case. The quality of an estimator can also be influenced by other factors such as its variance and mean squared error. The goal in estimation is to find the estimator that is both unbiased and has minimum variance, or in other words, has the best trade-off between accuracy and precision. Unbiased estimators are preferred over biased estimators as they provide a more accurate representation of the population parameter. Now, we shall look into certain examples for unbiased estimators. Suppose a government agency wants to estimate the average income of workers in a certain city. They decide to take a simple random sample of 500 workers from the city's population and use the sample mean to estimate the population mean income. If the sampling process is unbiased, then the sample mean will be an unbiased estimator of the population mean income. In other words, on average, the sample mean will be equal to the population mean income. To test for unbiasedness, the government agency could repeat the sampling process multiple times and calculate the sample mean for each sample. If the average of all the sample means is close to the true population mean income, then the estimator is unbiased. For example, suppose that after repeating the sampling process 100 times, the average of all the sample means is 50,000. If the true population mean income is also 50,000, then we can say that the estimator is unbiased. This means that on average, the sample mean income is equal to the population mean income, and that the sampling process is not systematically over or underestimating the population mean income. Suppose a car manufacturer wants to estimate the average fuel efficiency of their new electric car model. They decide to take a random sample of 50 cars from their production line and measure the fuel efficacy of each car. On average, the sample mean will be equal to the population mean fuel efficiency. If the average of all the sample mean is close to the true population mean fuel efficiency, then the estimator is unbiased. For example, suppose that after repeating the sampling process 100 times, the average of all the sample means is 80 miles per gallon. If the true population mean fuel efficiency is also 80 miles per gallon, then we can say that the estimator is unbiased. This means that on average, the sample mean fuel efficiency is equal to the population mean fuel efficiency, and that the sampling process is not systematically over or underestimating the population mean fuel efficiency. Consistency. In the theory of estimation, consistency refers to the property of an estimator where its value approaches the true value of the population parameter being estimated as the sample size increases. An estimator is considered consistent if, for any given population, the value of the estimator converges to the true value of the population parameter as the sample size becomes larger and larger. This means that as the sample size increases, the estimates become more accurate and closer to the true value of the population parameter. As estimator Tn is equal to T of x1, x2, etc. xn based on a random sample of size n is said to be an consistent estimator if for gamma of theta, theta in theta, the parameter space, if Tn converges to gamma theta in probability. Consistency is an important property of an estimator as it provides a measure of the accuracy of the estimator over repeated samples. A consistent estimator is more likely to produce accurate estimates of the population parameter, especially for large sample sizes. However, being consistent does not guarantee that the estimator will produce accurate estimates for smaller sample sizes. The goal in estimation is to find the estimator that is both unbiased and consistent, or in other words, has the best trade-off between accuracy and consistency. Consistent estimators are preferred over inconsistent estimators as they provide a more accurate representation of the population parameter as the sample size increases. Now, we shall look into certain examples for consistency of estimators. Let us consider the example as, suppose a company wants to estimate the average salary of all employees in their company. The company has 1000 employees and they want to use a simple random sample to estimate the average salary and to check whether the estimate is consistent. The following is the procedure. The company decides to take a random sample of 100 employees from their company. They collect information on the salary of each employee in the sample and uses the sample mean to estimate the population mean salary. Let us assume that the calculated sample mean salary is found to be 50,000. In order to test for consistency, the company wants to repeat the sampling process multiple times, each time increasing the sample size. They decide to repeat the process 10 times with sample sizes 100, 200, 300 and so on, up to a sample size of 1000. For each sample size, the company takes a new random sample of employees and calculates the sample mean salary. The company records the sample mean salary for each sample size and plots the sample mean against the sample size on a graph. As the sample size increases, the sample mean becomes increasingly close to the population mean salary. This indicates that the estimator is consistent. Now, to confirm consistency, the company calculates the standard error of the sample mean for each sample size. The standard error of the sample mean decreases as the sample size increases, which further supports the conclusion that the estimator is consistent. Based on the results of the repeated sampling process, the company can be confident that the sample mean is a consistent estimator of the population mean salary. This means that as the sample size increases, the sample mean will become increasingly close to the true population mean salary, and that the estimator is not subject to significant sampling error or bias. Let us consider the another example as, suppose a government agency wants to estimate the average income of all households in a certain region. The region has 10,000 households and the agency wants to use a stratified random sample to estimate the population mean, income and wants to check the consistency of the estimator. So, the procedure is as follows. The agency divides the region into 3 strata based on income: low, medium and high. They obtain information on the number of households in each stratum and their total income. The agency decides to take a stratified random sample of 300 households with 100 households from each stratum. They collect information on the income of each household in the sample and use the weighted sample mean to estimate the population mean income. They calculate the weighted sample mean income and find that it is 60,000. To test for consistency, the agency wants to repeat the sampling process multiple times, each time increasing the sample size. They decide to repeat the process 10 times with sample sizes of 300, 400, 500 and so on, up to a sample size of 10,000 is reached. For each sample size, the agency takes a new stratified random sample of households and calculates the weighted sample mean income. The agency records the weighted sample mean income for each sample size and plots the sample mean against the sample size on a graph. As the sample size increases, the sample mean becomes increasingly close to the population mean. This indicates that the estimator is consistent. To confirm consistency, the agency calculates the standard error of the weighted sample mean for each sample size. The standard error of the weighted sample mean decreases as the sample size increases, which further supports the conclusion that the estimator is consistent. Based on the results of the repeated sampling process, the agency can be confident that the weighted sample mean is a consistent estimator of the population mean income. This means that as the sample size increases, the weighted sample mean will become increasingly close to the true population mean income, and that the estimator is not subject to significant sampling error or bias. Efficiency. In the theory of estimation, efficiency refers to the property of an estimator that measures how close its value is to the true value of the population parameter being estimated compared to other estimators. An estimator is considered efficient if it has the smallest variance among all unbiased estimators of the same population parameter. Variance is a measure of the spread of the estimator's value around the true value of the population parameter. A smaller variance indicates that the estimator is more accurate and has a tighter distribution around the true value. If T1 is the most efficient estimator with variance V1 and T2 is another estimator with variance V2, then the efficiency E of T2 is defined as E is equal to V1 by V2 and E cannot be greater than 1. The concept of efficiency is used to compare different estimators and to choose the one that is most efficient for a particular problem. An efficient estimator has the smallest variance among all unbiased estimators of the same population parameter. This means that the value of the efficient estimator are less spread out and are clustered more closely around the true value of the population parameter. Efficiency is an important property of an estimator as it provides a measure of how well the estimator performs in terms of accuracy and precision. The goal in estimation is to find the estimator that is both unbiased and efficient, or in other words, has the best trade-off between accuracy, precision, and computational feasibility. Now, we shall look into certain examples for efficiency of estimators. Suppose a firm wants to estimate the mean daily production of a certain product in a factory. The factory has 10 production lines and the firm wants to use simple random sampling to estimate the population mean daily production and then check the efficiency of the estimator. The procedure is as follows. The firm obtains a list of all production lines and assigns each production line a unique number from 1 to 10. They use a random number generator to select a simple random sample of 3 production lines from the list. They select production lines 2, 5 and 9. They collect data on the daily production of each selected production line for a week and calculate the sample mean daily production. The sample mean is 500 units per day. The firm repeats the sampling process with different set of 3 randomly selected production lines. and calculate the sample mean daily production for this new sample. The new sample mean is 510 units per day. The firm repeats the sampling process multiple times, each time selecting a different set of 3 production lines. They calculate the sample mean daily production for each sample. The firm calculates the standard error of the sample mean for each sample. The standard error measures the degree of variability in the estimator due to sampling error. They find that the standard error of the estimator is small, which means that the estimator is efficient. To confirm efficiency, the firm calculates the variance of the estimator. The variance measures the degree of dispersion in the estimator due to random sampling. They find that the variance of the estimator is small, which further supports the conclusion that the estimator is efficient. Based on the results of the sampling process, the firm can be confident that the sample mean daily production is an efficient estimator of the population mean daily production. This means that the estimator produces a low level of sampling error and variance, and that it is an effective way to estimate the population parameter with a small sample size. To increase the efficiency of the estimator, the firm can consider using stratified random sampling or cluster sampling to further reduce the sampling error and variance. Summarization. In this module, we have discussed the concepts of estimation, tried to understand the terminologies associated with the theory of estimation. We understood the characteristics of estimation such as unbiasedness, consistency, and efficiency, which was defined and explained in detail by considering the suitable case studies. Thank you.